Uh, Thanks a lot, Adam, for this nice introduction. It's always a pleasure for me to be in CFT. So I'll be talking about the project I've been working on with a friend of mine and collaborator, Daniel, last 4 months, and the project is now upon completion. So I'm very happy that I can convey our results. So this is Daniel. He was a postdoc in Perimeter Institute, and recently he got permanent position in Federal University in Niterói in Brazil. Does any of you know where Niterói is? So this is a... Yes. So yes. So Niterói is close to Copacabana. Niterói is close to Copacabana. This is a town just across the bay from Rio. So this is a beautiful site. From Niterói is here to Rio, and okay, actually here you have Copacabana, and it was actually the most beautiful sunset I've ever seen there. But it was a great pleasure to work on this project as well. So let me start with motivation. Okay, question to you guys again. So what is this? What does this picture represent? Yeah, so it is an artist's impression of a quantum computer. We don't have quantum computer just yet. Everybody is waiting for them. And why? I mean, it is very hard task to build them.
But there are already the thriller books about quantum computing. They just bought
There is what? Sorry.
computer stuff.
Yeah, there are many things going on. The point is, yes, it's quite hard to build quantum computer in reality because of the noise and the coherence that inevitably affect quantum systems, and therefore one needs to use sophisticated procedures of quantum error correction that, in their current status, leads to huge overheads between physical qubits and logical qubits. So in order to implement one logical qubit, you need to use many, at the moment more than 1,000 of physical qubits. So we're not yet there by any means. Yeah, so people in the community came up, were wondering how one can use devices of intermediate size. Okay, so maybe we won't be able to do full-fledged quantum computing, but machines, small quantum, moderate-size quantum machines would be able to do tasks of restricted purpose that nevertheless would be still computationally hard. Even though you don't have full power of quantum computer, you can still have something which is computationally hard. And the advantage of such approach is that you, in principle, will not need error correction, and you won't have to stabilize your systems so much. So yeah, so this is partially does. Yeah, so it's a huge field. Yeah, so this is what my talk partially is about. Yes. So my project concerns boson sampling, which is actually one of such proposals that realize the so-called quantum computational supremacy. So the setup is very simple, at least to define. So imagine we have a linear optical network that photons can travel through it, and assume that, okay, by this array of beam splitters, phase shifters, I implement some linear optical unitary here, but the input state is a particular one, so I have a bunch of modes M, but first N of them, I just put single photons there. It is very important that those photons must be indistinguishable. So I'm in the regime in the realm of second quantization, And I put in such state to the network and then measure particles in the vacuum, nothing. Okay, and then I measure in the output, and I gather some statistics. So this is what Boson sampling machine does. Pardon? Yes, exactly. So it corresponds to such transformation of the incoming to outcoming modes. Yes, although like for it to be maybe meaningful, you need to have many photons, and that's the yeah. So far, what do you?
No, I mean for the presentation.
For the presentation of the picture, I cannot plot 10,000 photons. Yes. So yeah, the task of the boson.
You have also to check whether there was a photon repeat.
No, this is not. I will go back. I will go to this question in a second. Okay. In principle, there is no need to do something like this. So this boson sampling machine, what it does, it samples from some distribution on the outputs. Okay. And the claim, let's say, complexity theoretic claim is as follows. So up to some complexity theoretic conjectures that I will comment in a second, it is unlikely that there would exist a classical machine that would produce samples from distributions that are close to this boson sampling distribution for typical unitaries U. So this is the claim. Like if you assume some computational, yes?
Well, I don't know whether it's a good problem, but suppose I have a billiard table
Yes.
with a certain number of holes. Usually there are 3 of them on one side, right? And on the other I bore more holes, right?
Mm-hmm.
And I set the billiard balls across and I cover the table with something so I don't see what happens. And there are elastically scattered pieces of wood put inside. So they scatter the balls and the balls which have been set can emerge to the many other balls. What's the difference?
Well, I mean, here you
The sampling will be precisely the same. You set 3
so why did you? No, not. No, that's the whole point. That it's very important that those objects here are indistinguishable. Okay, and it's not the same, Professor. No. No, I mean, although that's the whole point that you really need the indistinguishability.
No, but also here, he's doing mixing on the level of probability.
Yes. So everything is supposed to be coherent here. So I don't. The whole talk is about losses, but there are not losses just yet. But coming. This probability, right? So let me explain. So it is modulo some conjectures. It is unlikely that there would exist a classical machine that would produce samples from a distribution that is close to this boson sampling distribution in the time which is polynomial in n, the size of the problem, and the inverse of the epsilon. And epsilon is the error tolerance that you allow for. So, okay, this TV here this is an important number. This is total variation distance between 2 probability distributions. So, I just maybe write the if I have one probability distribution pi, another qi. Let's say this TV distance between them is the sum of the roughly sum of the moduli of all of them. Some measure of distance between densities, okay? Which is related to oh, okay, yes. This is just a matter of convention. Oh, I don't see the square. Yes. So this is some measure of distance between probabilities. Okay, and yeah, it is important that you assume for the moment that you can measure actually the output numbers. Yes. I mean, you can have more. It can be. It can be two. Yes. Yes. Although in the regime, which is interesting, it typically happens that it's very unlikely that you have more than one there. You have like inverse of photon bunching actually. When you have like many, like when m is much bigger than n, let's say, roughly. Yeah. Okay. So that setup, okay, was introduced, I should have mentioned, by Scott Aronson and Alex Arkhipov like a few years ago, and it attracted a lot of attention. So it's no. So it's unlikely means that in classical complexity theory, you have unfortunately many conjectures. Like it's not known if P equals NP, and there are different complexity classes there. And people, let's say, conjecture that some of them are different. Okay, so so this is the status. For instance, it is not known if quantum computers are more powerful than classical ones, because those things have not been proven on the realm of classical complexity theory just yet. Okay? So this is the status of computer science, if you wish. Unfortunately, no, but let's say you... Mm-hmm. Not that I'm aware of, sorry. Okay, so the specific conjectures that I mentioned, they have to do with so-called polynomial hierarchy, which is, roughly speaking, the generalization of the P versus NP problem. So you have the whole like tower of complexity. Yes? Yes. To prove hard, yeah. Okay. So yes. So if I of course, that's the whole. Yeah, professor has very important point, but it's not known how powerful classical computers are. People suspect that some things are hard, some things are. Yes, so people don't know how powerful classical computers are. They suspect that certain problems are difficult, but they cannot prove it. They don't know how to prove it. Okay, and so these are the conjectures that I had in mind. Of course, yeah. Okay, so if you allow me, so those conjectures have to do with so-called collapse of the polynomial hierarchy, and with the fact that it is proved actually that computing of permanence of large matrices is hard. So it so happens that the transition amplitudes here, the output probabilities, they are expressed in terms of permanence of some matrices, and that plays important role in the sort of proof of this result. Okay, so that approach let's say, drove a lot of interest because independently people developed so-called integrated photonics. So they were actually able to like implement such chips for moderate sizes of the system. So the state of the art is that you have just a few photons in the input here, a bunch of modes, and it's okay. The question is it scalable? Okay, yes. On the other hand, classical simulations, very recent ones, can simulate up to 50 photons on a supercomputer. Yes. So the question that I want to address in this talk: is it possible to scale up such experiments? Yes. And basically, the take-home message that I want is that, like, if you allow for some losses entering the system, then the processes that you are getting would be classically it would be relatively easy to classically simulate them, subject to losses. So it will be, yeah. So my talk is about this. Yeah. So we pass through the motivation and the introduction of boson sampling. In the rest of the talk, I will present like main technical tools that I'll be using and the idea of this classical simulation that I mentioned. And then I will present results on classical simulation of lossy boson sampling for the model of loss when just fixed number of particles is lost, when you have a so-called uniform beam splitter model of loss, and for general lossy linear optical networks. So that's the rest of the talk. So now there will be no complexity theory, don't worry, it will be physics and like properties of quantum states and things like that. So the relevant Hilbert space that describes the system is the bosonic Fock space that corresponds to a certain number of modes. And it's important that you can look at it both from the first and second quantization perspective. So you can either have creation and annihilation operators, or you can think of this Fock space as a like direct sum of symmetric subspaces of distinguishable that describe certain number of indistinguishable particles. Okay. Typically, yes. No, so that's the no, but the whole state. The point is you shouldn't have any other degrees of freedom. So the input state, this is actually important. The input state. So the input state, let's say you assume that, for instance, polarization is fixed. Okay, you don't have you just have path degrees of freedom, and the input state is just arrays of ones. So photons occupy just first and modes. Okay, and it is important that you don't have any other degree of freedom, for instance, polarization. Yes, it's at the same time. Yes, like, it's very important that they are like synchronized and so on, right? Yes. Okay, and typically let's say we'll be studying cases when the input state has n particles, so just belongs to one particular sector of this Fock space. And as I mentioned before, in the language of second quantization, the linear optical transformation is described in this way. But in the first quantization, you can just treat this thing as, let's say, the same unitary operation applied to every particle. Of course. I'm just saying, the point is people in the community focus on this description, like 99%, which is, yes. Although the whole point of our work is that you can gain something from this description. And this is what we are exploring, actually. Yes, and so as I mentioned, this fixed particle sector can be embedded in the system of many distinguishable particles, and that gives rise to like particle entanglement. Particles can be entangled here with respect to the cut of the Hilbert space presented here.
Now means that you will be dealing with mixed states.
Yes, yes, yes. I mean, I'll be having losses, so things will be mixed almost.
It's not equivalent. You cannot describe it.
Okay, so yes, if I have it, let's say for every n, let's say for every n, and if for every state row with fixed number of particles, I have such a presentation, then it's equivalent to this. I still can. Yes. I can write everything in terms, like any operator in this space, as far as, can be expressed as, let's say, polynomial in them. So, yeah.
Polynomial, but not a linear transformation.
What?
Not a linear transformation, but a polynomial.
I mean, those descriptions are really like, okay, so this is somehow in the Heisenberg picture. This. Yes, everything is. No. So I didn't talk about the losses just yet. This is lossless case. But the states are mixed. The state can be mixed. Yeah. Yes. So I can have particle entanglement, as I mentioned. And mode entanglement that corresponds to the cut of this Hilbert space onto so my mode labels different particles. Well, mode entanglement is like the entanglement that you have in optics typically when you have when mode gives you a degree of freedom that distinguishes a particle.
But this wave function entanglement, not the mode. The modes are fixed for a given system.
So it's mode dependent. The notion of mode entanglement is mode dependent. Given the choice of modes, so it's.
This is not entangled, but maybe center of mass is entangled to the relative.
Yes, exactly. So this is, so it's mode dependent, but sort of setup gives you the what it means. Yeah, setup gives you the mode somehow. Okay. Okay. So important role will be played by particle separable states. So those are states. But like if you have, well, I guess when you go to experimentalists, it really matters what are the modes that they are studying, what modes couple to given optical fibers, etc. Sort of physics experiments give you distinguished basis.
That is true what you said, but it doesn't follow from the description.
But I didn't want to mention it. Like, sorry. So n-partite bosonic state is particle separable if it can be described as a mixture of condensate states. So every particle is is in the same state, phi alpha. Okay, so it is very easy to update states of this form because, as I mentioned, they would just involved by the action of u to the power n, or it's depicted here, and it so happens that in this boson sampling scenario, the output statistics for such input state can be efficiently simulated classically. It would be just basically sampling from multinomial distribution. So you have, or to put it even simpler, so you just apply. So the simulation would go like this. So you have one state phi, you apply to it unitary u, then you measure in which mode the particle is. You have some probability to get it. Then you sample another particle, you gather the statistics, and this is the simulation. It's very simple. Doesn't scale exponentially with the size of the system. And then, if we additionally assume that this distribution here, this p alpha, you can easily sample from it, then this whole state would be easy from the perspective of boson sampling. Phi alpha is a single particle state. Like state of a single, I have n particles, it's a state of, it's a single particle wave function, yes. So,
And then you take the product of the
yes, yes. And it is, so, what is important in this slide is that the sampling from output distribution from such a state is very easy. And also up to some things here, sampling from output distributions from such a state is easy. Right, so that this is important to remember. And now the losses. So one model of losses is very simple. When you start with n particle state, you can trace all but L particles from it. Now I'm using first quantization language. I'm getting some state on L particles. This is one model. The second, maybe a bit more. So I assume that the chance of losing a photon from every mode is the same. But it's, and I know that in total I lost fixed number of particles. So that would be the map. But maybe the more realistic model is the one when particles are lost with some fixed probability from every mode. Okay? And this probability, let's say, is 1 minus eta. So physically, you can imagine that you have, before your unitary, you have an array of beam splitters that scatter your light to some degrees of freedom that you don't monitor. Okay? But it is important that this eta is the same for all beam splitters, for now at least. And then this is the density matrix that you obtain. It's just like a mixture of those rho L's with the binomial weight. Okay. Finally, the most realistic model is the following. So, in order to implement big unitary in this linear optical setup, you actually have to concatenate beam splitters phase shifters. So you have linear optical elements that couple just few modes at the time. And then we assume that upon when those operations act, they are actually associated to such beam splitter guys, but just they just act to they are just associated to the modes when this linear optical element acts. And it is okay. It is now important that you cannot here. You can check the mathematics that this array of beam splitters you can put beside you. It commutes with this mapping. But those guys, they won't commute. So you cannot, in general, you cannot pull out all those losses in front. So this is some complicated map. And we are studying in this work all those things, and also this, which I'm very happy from. Okay, so now let me give you that is another important slide. So here I outline the main the main idea of classical simulation strategy that we have, illustrated on this case when we have fixed number of particles being lost. So remember, if I had yes, exactly. Because in physical implementation, you can have photons or particles. Physics, actually, it's maybe easier to implement it with photons. Yeah. Depends on the preference of a listener and the speaker. So this is the input state. And now when I lose n minus L particles, I'm going to be left with the mixture of states that have different L's in different registers here. Like, okay, so for instance, when I have such a state, and I lose just a single particle, I will have, as a result, convex combination of a state when I lost particle here, a state when I lost particle here, and so on, right? No, it's a mixture. It's a mixture. It's just important. That's why I said that we have mixed states. Yes, so just 0.
And also using density matrix approach is useful because if you state creation relational tables with noise terms in the
Yes, I mean we use both first and I mean it's the same. We use mixed states, of course. I mean it must be described by mixed states. Yes, okay. So this is the input state. Now the input state when I have L particles, and now the idea is that I would be approximating. So this state in general won't be particle separable, but it might be close to being particle separable. So imagine that I have now the body of all states supported on L particles, and I have this class of particle separable states that I depicted here. It's a convex set. And this is my state, input state rho Ln. I would be trying to find the state from the separable set that would be closest to it in the so-called trace distance. What is trace distance? It's some measure of a distance on the set of states you can understand it as sort of optimizing this total variation distance over all measurements that you can apply to your states. So it is only important that it's an upper bound on top. So if I have two states, rho and some sigma here, the trace distance, the total variation distance between the corresponding probability distributions would be upper bounded by the trace distance. Okay? Even after I apply this unitary U to everything. So it is important. So if this delta Ln, the distance of my lossy state to a set of separable states is small, then I know that the corresponding probability distributions will be close. On the other hand, as I explained earlier, the state here, the output statistics of the state here would be classically simulable. Okay? So wrapping it up together, if I find the optimal sigma star, the closest separable state to this lossy state, that gives me immediate classical simulation of the boson sampling to the accuracy exactly delta Ln in this total variation distance, which is the figure of merit for this problem. And
there's no guarantee that which is smallest, that it will be
of course, and this is what the, let's say, merit of this work is, to compute those things. This delta Ln, yes. Yes, so this is, let's say, our first result that concerns, again, this model of loss when you use fixed number of particles. So I'm left with L particles, and this delta Ln is the distance to the symmetrics, to the separable states. And it's nice that we can actually compute, we have a single letter expression for this distance. It's described here. So n is the total number of particles that were present in the state initially. L is the number of particles that are left. It's some complicated expression. I will come back to it in a second. But the state that approximates... sorry? No, but the point is you don't, like, just staring at it, you don't look if it's big or small. At least I don't have such experience. Yes, of course. Yes. But it is also nice that the inputs, the closest separable state has a very simple interpretation. Forget about this expression for a second. Imagine the following process. So I take my wave function to be single particle wave function to be like superposition with equal weights of the mode basis. Okay, and now let me just apply arbitrary unitary that imprints phases here. Okay, and then I take, so this is written here. Now I take tensor power L, and I repeat. So those phases here were random. We're taking uniformly at random, and I average, and this is the state. I mean, it can be written also in different form, in decay basis, and so on. But so that gives you already the scheme how the classical simulation would go. You would start from such a state, apply those phases, then apply the unitary, and then gather the statistics by averaging over those phases. Okay, but it is important to, I mean, this delta Ln was supposed to be small. So one has to do the asymptotic analysis of what is going on. I mean, for the classical simulation to be working. So if you do the asymptotics, so if this number of particles that are left scales, sorry? It depends on L and N. So if L is... No, small, this total variation, small, it's compared to 1, because this distance is between 0 and 1, let's say. So this, if this L grows slower than square root of n, then asymptotically, this is the expression for this delta. So if L would be growing slower than n, the initial number of particles, it would tend to 0. On the other hand, if it's larger asymptotically than square root of n, this delta would go to 1. Okay? So this is the regime when the classical simulation can work. In this model. Let me now move to second model, when I have a beam splitter model of loss. So it's similar in a sense that I have again the same, like now I have convex combination of states of the same form as before. So now we just take the guess that instead of taking this, that we take the same mixture, but here for given number of particles being left in the network, we take the same optimal state. Okay? And effectively, as you can of course expect, so that corresponds to this distance, to this trace distance between this state, this lossy state, and our approximation. That just corresponds. So I have this formula that depended on n and L previously. Instead of L, I just have to substitute the average number of particles that are left in the network, which is eta times n. Okay, so effectively the same results hold. But okay, that was very nice because I could shuffle around those losses before and after the network. But in the actual network, I have this complicated array of beam splitters, and I don't know how to cope with this. So the autumn last year in Sopot was very nice, and I was walking in the cellar, and finally some idea came to my mind. And I'm very happy that I can convey the result. So this is the lossy network. So I have those beam splitters in front of that are lossy. And it turns out that what you can do, you can pull out certain uniform number of losses in front of this network. Okay? And how many losses you can pull out would actually depend on the shortest path that a classical particle, shortest number of times a classical particle takes to pass, shortest number of times a classical particle passes through a beam splitter as it passes through the network. So it's a very geometric object. So in this case, the smallest number would be 2. Like you can, if the particle goes here, it will be just 2. If it goes like, if it arrives at the beam splitter, it can go either straight or change the mode. If it goes like here, let's say it would be 4. So the relevant parameter would be the shortest number of times a particle has to pass through a beam splitter as it passes through the network. Okay, so and then I can pull out certain strength of losses, and this is what this theorem explains. So let S be the smallest number of times a particle traverses through a beam splitter as it propagates to the network N, and then let this lambda N be a channel associated to this network. Then I can represent this channel as a composition of the equal beam splitter model of loss and some other linear optical network, lambda tilde N, where this effective strength of this loss, okay, would be let's say probability of photons being left in the network is like square root of m times eta to the power s. So eta was a strength of a single beam splitter here. So it scales exponentially with s. So the smaller this number, the more lossy you are. Okay? So it's okay. I think it's a very nice result because it works irrespectively on the, let's say, geometry of the network. Okay, you can always pull out many losses. So even one can think that, oh, by triggering those things together in a clever way, maybe you can mitigate the losses in some sense, but you cannot in some sense. I mean, to that extent you cannot. Okay, m is the total number of modes. And the result then is that by repeating, so to this guy, I can apply the same reasoning as before and get a classical simulation. So this is the result. So if I have this shortest number of times a particle passes through a network, then this is the accuracy to which I can classically simulate my output statistics. And it scales. Efficiency means that scaling, let's say, polynomially with the size of the system on a classical computer. In practice, the polynomials are very low degree. Okay. So let me stress that the scaling is exponential in S. And coming back to boson sampling, to typical implementations of boson sampling, you require there that this number of modes scales like n squared. And typically this S is much greater than n. And then even when this S scales logarithmically with number of particles, which is a small number, you can still get this distance, your accuracy going to 0 for fixed. Let me stress this, for fixed transmittivity of a beam splitter. Okay, and this is like another main result that we. Well, it's like efficient. Well, okay, you can, if you allow for. Well, efficient. Okay, but there is a discrepancy in the classical complexity theory. Let's say between what is efficient in practice, okay, and efficient. So I know. Okay, we didn't run the numerics, but the algorithm is actually very. Simple and yeah, so I guess we can simulate. I guess easily we can go to thousands easily, because it's like how the simulation would go. I don't have it maybe unfortunately on site. So you would take so if you have, let's say, 1,000 modes, you would take equal superposition you have 1,000-dimensional Hilbert space. You will take equal superposition of states there. And then you would apply unitary, 1,000 by 1,000 unitary. It's possible to do on a classical computer. Then you would read out. Read out the amplitudes. Okay. Sorry, I forgot. You have to imprint those random phases, which is also easy. Then you apply this unitary. Then you measure. Then you read out the amplitudes. It's still easy. And then maybe what you have to do, you have to maybe toss again. You would have to sample from a binomial distribution to know what is the number of particles. Yes, yes, yes. No, but the difficulty is like it is the aim of the game is actually not to get the distribution, because it's going to be very hard because you have many outputs, but to produce a sample at least. So this is actually in the. Sorry.
You want to replace the quantum computer with a classical.
Yes, yes. Yes, of course. But cost of preparing a sample from this distribution would be hard, and it would correspond to one run of experiment. Like, I mean, you'll have to average over many realizations, just like in experiment. And yeah, so it's efficient. We can discuss more about it, but yes. So okay, I managed to get almost to the end of my talk. So let me summarize. So it turns out that complicated linear optical networks are heavily affected by losses that occur there, no, but I mean in the quantitative sense that I described, right? So in particular for the boson sampling devices, if you assume that you are left with just square root of initial number of particles or less, then this is the accuracy to which you can efficiently simulate the outcome distribution. And if you have more complicated network, this is the formula for the accuracy. And for fixed eta, it scales again exponentially with S. And aside from the boson sampling application, that puts a limitation on constructions of more complicated linear optical networks, because you will have always this exponential factor if you have paths that travel through many beam splitters. So yes, so these are the main conclusions of my work, and let me maybe finish with open problems. Okay, so the first one you might not be that interested in because it concerns the complexity theory. So in the original boson sampling formulation, this error tolerance was supposed to be arbitrarily small, and the machine should just work for every range of epsilon, maybe on the cost of using more time. Okay, so this machine, our procedure doesn't do it. This tolerance is our guarantee for the tolerance is fixed, let's say. Okay, other direction of further research will be to use, instead of the trace distance, actual estimates on the total variation distance between probability distributions. That can give stronger results. Also, I think a lot can be done if you would try to do similar things, but not on the balanced beam splitter model, but for for the cases when certain modes are more lossy than others, and the similar techniques should apply. Also, we had this factor square root of m in front of the effective loss that you can pull out from the network, and this is really an artifact of the proof, and I don't know if it can be removed or not. So for maybe not for boson sampling, but for other practical applications that might be relevant. And there is a bunch of other quantum computational supremacy proposals out there. Actually, just this morning I checked that IBM announced a 49-qubit quantum computer, but they don't claim that it would solve something practical. They want to demonstrate again this quantum supremacy in the sense that I was talking about. They have some sampling problems that are different than boson sampling. But I'd like to check if similar techniques can be maybe applied there for other proposals for quantum computational supremacy. There are zillions of other problems. If you want to work, I'm happy. With me on those topics, I'm very excited. And thank you for your attention. And next week, the paper would be on archive. So stay tuned. Yeah.
I'm coming back to your idea to replacing a quantum computer by the classical one. Suppose I want to solve a problem of finding whether the number is prime. I more or less know how complicated this is for the classical computer. I have some algorithms. People use these algorithms, those who crack codes or whatever. And we have something like a Shor algorithm, right?
So
which
just,
will be implementable on the computer.
So just
suppose you want to replace now this Shor algorithm and this quantum computer by your machine, and then you compare the efficiency in time the computer will run using this classical solver for prime number or this your quantum.
Yes, so the efficiency of those quantum, it's by no means my idea. Like quantum supremacy proposals are not my idea.
I'm not asking who had
yes.
I'm asking a simple question.
Yes, so the deficiency of those ideas is that they unfortunately do not solve concrete problems. In a sense, they
Thank you very much.
No, but can I finish? Because it's
okay.
but they are
This word about supremacy seems to be
well in the computational theory sense. There are other proposals for advantage. The other ones are quantum simulators, although it's like a balance of things. So the most trustworthy thing is a quantum computer when you have those algorithms for which you don't know the corresponding efficient classical counterparts. Quantum simulators, they solve things that are practical in the sense that they simulate quantum many-body states, and that might be practical for zillions of purposes, although it's difficult to prove their difficulty in the computational theory sense. Those things I was talking about here, they are the middle ground, because maybe it's easier to prove something on the computational theory side, but they have the drawback that they are they don't correspond immediately to something practical. Although some people are, as far as I know, work on this. So it's like, this is the state of the art of the field at the moment. I'm sort of, yeah. You can like it or not, but...
guess that what this Canadian sort of quantum computer
D-Wave.
actually D-Wave is actually using your tricks to do the...
Okay, yet there is another, maybe another approach, which is to do heuristic, like D-Wave does, so you don't have the, and it might be that by doing heuristic you can do something which would be actually meaningful, although you may not have actual hard proofs. Sorry? I have rough idea. I have some rough idea. I mean, heuristic in a sense that because you don't have the assessment of the noise and the degree of the coherence that affects your system, you don't know, let's say, so they treat it more like a black box. They don't really know what is going on inside the machine if they scale up the thing. And they are forced just to observe what is going on. So to some extent, yeah. Big, yeah.
There are tests run by, for example, by Dangara on the supercomputers on the D-wave regime,
Yes.
and they can be compared.
Yes.
They show that the D-wave too much.
But I'm not saying that it's.
In most of these tests, it doesn't work better than
Uh,
the normal computers.
yes. I mean, when I said heuristic, I didn't mean.
That indicates something
That indicates that the role of noise is predominant there. So at the moment, as far as I know, quantum, D-wave doesn't offer quantum advantage. But maybe if they invest more money and build bigger thing, maybe it would. Personally, I'm skeptical about it. But yeah.
But in other words, you are not guessing that what the D-wave does, it simulates a quantum computer in a classical way. That's the question.
So it doesn't. First of all, D-wave doesn't, to begin with, simulate quantum computer. It doesn't aim to, as far as I know. It aims to solve particular problems. Yeah.
No, they claim this is a general purpose computer.
No. Oh, maybe they were claiming some time ago, but not anymore. I guess they don't. Yeah. There was a huge discussion about it in the community.
Problems which go in the portfolio that Dangara's tests, because he runs them on that computer.
Yeah. So it's a quantum.
Publish the results. So
It's a quantum machine, but okay, it's maybe a technical. If you call it quantum computer or not, for specialists, it's not quantum computer. But
Okay, any other questions? If no, let's thank Michał again.
thank you.